In this video, we're going to show you how to add a simple timing circuit to the comparator circuit. It'll also serve as an introduction to capacitors. So you're going to need to find this 1000 microfarad capacitor in your parts box. It's kind of a convention for capacitors to be labeled in either microfarads or picofarads. So you'll see engineering notation maybe not exactly followed here. So it's 1000 microfarads is the value we're going to use. Yes, that is 1 millifarad. It's just not noticed as that. 35 volts is a rating. We'll talk more in depth about what that is when we study them. Do use your safety glasses for this introduction because this is an electrolytic capacitor, and it's one of two types that actually have polarity. Notice the one lead is marked with a minus sign. That absolutely must be followed, or the capacitor can explode like a firecracker. So what we're telling you is this wire here, this lead, is the negative lead, has to be the more negative lead, and this one has to be the more positive lead. Electrolytics have polarity that must be followed. That's what this is. There's another type called tantalum capacitors. They also have polarity. Those are the two types of capacitors that have polarity, and the polarity must be followed. So wear your safety glasses in case you mistakenly connect it the wrong way and the thing explodes. So what is a capacitor? A capacitor is basically two metal surfaces placed very close together with some insulation in between, known as a dielectric. So it is just a 2-pin device, and what happens is you can charge up those metal surfaces with coulombs, and they are known as the plates of the capacitor, the two metal surfaces. So very simply, if I took some voltage source and connected it to the capacitor, that capacitor will be charged up to the same voltage level as the voltage source that I connect it to. So if I had 5 volts sitting here, slide that over a little, the capacitor will charge up to 5 volts as well. What's going to happen is current is going to initially flow onto the plate. Conventional current will push positive charge onto this plate, okay? And like charges repel, so positive charges are going to be pushed off this plate. Also, they're going to be attracted to the negative side of the voltage source. So this plate is going to gain positive charge, and this plate is going to lose positive charge, and resulting in a negative charge. And while the capacitor is charging up, it does look, for the moment, like current is flowing. Well, it is flowing, but what I want to alert you to is it is not flowing through the capacitor ever. It's flowing onto one plate and off the other plate. And that is a big difference between actually flowing through. So do know that no current actually flows through, because that's an insulation there. That's the dielectric. So you do not get current flowing through the capacitor, but you get it on one plate and off the other. And once the capacitor is fully charged, where you would have the full 5 volts, then current stops flowing. It can't flow anymore. I think you can see for a couple reasons. The 5 volts that the capacitor is now charged up to is in opposition to the original source voltage, so there is no net voltage anymore to push charges onto or off of the plates. The other thing that you can always rely on is the fact that we said from the beginning that this capacitor is made up of two metal surfaces with an insulating layer between. If that looks like an open, good, because it is an open. And you cannot have current flowing with an open that is a sustained current. So it's a little bit of a new thing to consider, where we have an open, but we have metal surfaces so close together that they can charge up. They actually assist each other in a couple ways, because the positive charges push positive charge off, and then the opposite charge plates have an attractive force. So there's a lot going on, maybe sort of at that physical level, to look at. We can control how fast the capacitor charges up simply with a resistor in the circuit. So here would be a good place to put a resistor, and now in fact, depending on the value of that resistor, I can control how fast the capacitor charges up. The size of the capacitor also affects how long it takes to charge it all the way full. And I mean, you can think of the capacitor like a bucket in that sense, and you can think of the resistor maybe as the valve for the water, so like the faucet. So if you were going to fill a container and control the flow of the water, how fast it's coming out of the faucet, you can see those are your two factors. This controls the flow rate, and this is how big of a container you have. So the two together determine how long it takes to get the container full, if you're thinking sort of with a bucket analogy. And in fact, since those are the two factors, you can multiply them together, whatever resistor you're using to charge the capacitor and however large the capacitor is that's getting charged. You multiply them together and you have what's known as a time constant. And that will be consistent, and we'll show you what we'll do with that. The time constant that you get from multiplying your charging resistor times your capacitor size tells you the time in seconds that it's going to take to get to 63% full charge. Or if you were discharging the capacitor, which we'll talk about in a minute, as in once you have a charged cap, you could empty it just like you could a bucket, if you had some kind of a analogy going there. It would be the time it takes to get it 63% of the way to empty. Okay. So again, that time constant is given in seconds, and later on we'll understand in more detail how resistance times capacitance actually gets you seconds. Might seem strange. Seconds are in there. It has to do with current, which is coulombs per second. I probably should have mentioned right from the start that capacitance is measured in units known as farads after the researcher Michael Faraday. And so that's the units for capacitance. And capacitance is really a measure of how many coulombs you can fit onto the plates with given a certain amount of pressure. So it's actually coulombs per volt, but we'll study all those details down the road. So capacitance C measured in farads F, and a farad is a very large amount of capacity or capacitance. A 1 farad capacitor could store 1 entire coulomb of charge on its plates with only 1 volt of pressure pushing it on there. That's how much room it has. I think the next thing we should do is just talk through the charging of the capacitor step by step. There's a couple more details to look at. If we start with a capacitor that has no charge on it, it has 0 volts across it. And when you first apply the 5 volts, you can see, I think, that all the 5 volts will be across the resistor and the cap has no charge. Now immediately that's going to start to change. And I want to show you how the capacitor charges. It does not charge linearly. It actually starts off charging rapidly, okay, and then slows down. So it's like an exponential curve. Let's show you that. And this is always the shape of a charging capacitor. Something like that. You see how it's charging quickly? It's gaining voltage very rapidly at first. And that should make sense because we have the maximum voltage across our charging resistor, which we know with Ohm's law means our maximum current that's charging the cap, that's pushing coulombs onto the plates, it's the highest right in the beginning. So the voltage is climbing most rapidly. And as the capacitor starts to fill up, just like anything else that you can maybe think of some analogies, the fuller it gets, the harder it is to push more charge or more coulombs onto those plates. I always joke about taking a capacitor lunch. You know, it's like you or I, if we're eating, as you get fuller, you start eating slower, right? Maybe that might be a strange analogy, but helps you remember that take a capacitor to lunch and watch it eat. It'll start slowing down. That might be the strangest analogy I've ever come up with, but okay, it's one anyway for you. Of course, another way to understand this happening is to look at the voltage across the resistor. Look, you have two components in a series circuit here, and you got 5 volts for the source for our example. So it should make sense to you that as the capacitor gains voltage, the resistor loses voltage, which means current's going to be decreasing as the resistor's voltage drops. So if you can see, maybe we'll just fast forward to like a midpoint here. There'll be a point in time where the capacitor is charged to 2.5 volts, and notice the resistor only has 2.5 volts, so obviously current's slowing down. And we could track the whole way through that, and you can with your oscilloscope. I mean, here we have the scope's ability to trace voltage in time. Time is the time is the horizontal axis, the x-axis, and voltage is always traced out on your scope vertically. And you can map it through. I mean, there's going to be a time when the capacitor has 1 volt, and of course the resistor at that time will have 4 volts, and then the capacitor has 2 volts. The resistor has 3. 2.5 volts and 2.5 volts and so on. Then the capacitor up 3, the resistor up 2, 4 and 1, 5 and nothing. In fact, we can watch, if we look at the resistor's voltage, it's going to be just sort of a mirror image of the capacitor, right? It's going to start out high, maximum current, and then decrease inversely, you know, at the same rapid rate as the capacitor's voltage is increasing, the resistor will decrease. So you're going to have something like this. Okay? And that would be the voltage across your resistor. It is just a series circuit. So whatever voltage the cap has, plus whatever voltage at any given instant is on the resistor, we'll always add to 5 volts. So this voltage plus this voltage, you know. Here's our 2.5 volt mark. Put some little marks on here for you. You know, that will be the 2.5 volt. It's hard to squeeze stuff in. Up here would be our 5 volts, right? Here's our 0 volts. And so on. I'm going to switch gears on you just a little bit. I remember we're going to run this experiment on our small breadboard. So 3 volts is what you'll have. Might as well put some actual numbers that might help you recognize them when you get them up on your scope. So if we do have a 3 volt source, obviously you can charge the cap up to 3 volts. And the main thing I want to get across to you is it's not linear. It'll start out rapidly at first and then slow down. And we can see the reasons why that happens, because as the capacitor is gaining voltage, the voltage that it's charging to is in series opposition to the source. So it's starting to cancel out the net voltage for the resistance that's used to charge it. So you can see that happening. The cap's gaining voltage. The resistor then, of course, is losing voltage because of the net voltage that's across it. You know, like we said, when the cap has 1 volt, it's going to cancel with the 3 volts and leave only 2 volts for the resistor. So the series opposition is one way to look at it. You can look at it as a series circuit. You can even look at it as a voltage divider. All those things are valid perspectives. But we mainly want to show you what the classic charging curve of a capacitor is. It'll always be nonlinear. It'll start out fast and slow down. Current will also start out high and decrease to 0 current when the capacitor has the 3 volts. We said before, you can't have any net voltage then across the resistor. We mentioned before that you can multiply the resistance of the charging resistor times the size of the capacitor that you're charging up, and you will get the time in seconds, R times C, ohms times farads, right here. You get a time in seconds, also known as the time constant, but this is how many seconds it will take the capacitor to get to 63% of full. 63% of 3 volts is 1.89 volts. A little less than 2/3 of the way to the full charging voltage. And again, we got that by simply multiplying the resistor times the capacitor, known as the time constant. And that's this time that you can literally see. And if you put your scope in slow scan mode, we'll be able to see that. We'll be able to see the time in seconds from here to here on the scope screen match up to this point on the charging of the capacitor. When the capacitor gets to 1.89 volts, this much time will have elapsed, R times C. We can use some real easy numbers actually to illustrate that. And I think what I'll have you use is that large capacitor so things happen nice and slowly. So for example, we had that 1000 microfarad cap. Make sure you got the right polarity when you put that in. And let's put in like a 10K resistor here. And do you see what the time constant is? If I multiply 10K times 1000 microfarads, do that. The time constant for this circuit then is 10 seconds. So it's a nice slow charging that we can observe, happening in real time. So we'll show you in a minute that little circuit that we'll put together, but that's basically it. We'll put a switch in there so that we can start it when we want to, but we'll have the capacitor in a discharge state. That'll be another important thing to establish. It has to be starting at 0 volts right here. And then when we throw the switch, we'll connect the capacitor to the 3 volts through a charging 10K resistor. And right on your scope before your eyes, if you have it in slow scan mode, you'll see the capacitor charge, and you will see this many seconds right on your screen. For example, if you set the horizontal scale on your scope for 5 seconds per division, those little blocks that show up on your scope. If I could do that a little better, but 5 seconds per division, right? You would see this show up to be one block and another block, and after that second block, the capacitor would be at 63% of 3 volts right after 10 seconds when you're using a 10K and a 1000 microfarad cap. Not a bad intro to pull all that together in a nice slow-mo way that you can see it happening. You might be a little curious about this point right here, the halfway point, right? When the capacitor is exactly halfway towards full charge, and also the current has fallen to exactly half of what it was initially. It's slowed down to half. That point happens not at the time constant of 10 seconds, but it happens at 0.7 times R times C, or 0.7 of the time constant. For our example, with a time constant of 10 seconds, this midpoint, if you want to call it that, would occur at 7 seconds then. So you can look at that on your scope too. That should all be easy to display. When we get to that point, in case I forget to remind you then, you can hit the stop button on your scope. It'll stop acquisition and freeze the display. So sometimes that's what you might want to do. If you throw the switch, the cap's charging, you see all this happening right before your eyes, and you want to keep it on the screen, simply hit the stop button. It'll stop acquisition. Just this little introduction to capacitors again looks like something that would be good to be caught doodling at a coffee shop, right? It's kind of impressive. It's simple, but every little thing is important. Just a couple more things to get squared away. The schematic symbol for an electrolytic capacitor that we're using actually has this curved symbol for its other plate. A non-polarized capacitor, in other words, it doesn't matter which side is positive and which side is negative, just has the two straight lines. So we are using an electrolytic. So let's get the schematic symbol properly drawn. And I want to show you, after you've charged up that electrolytic capacitor, it'll have the 3 volts And theoretically, it would always have them, always have that charge. It'll hold that charge. So I wanted to sort of really impress that upon you. And the only reason it loses that 3 volts is the insulation might not be absolutely perfect between the plates. So there might be a little bit of leakage that equalizes down to 0 volts over time. The other factor that affects how long that capacitor will hold its charge is maybe how conductive the surrounding air is. So if there's humidity in the air that allows a tiny current, this 3 volts that the capacitor is charged up to will find ways to equalize very slowly, but it will lose its charge. Because remember, the bucket analogy is pretty good. Remember, it does not have the ability to generate a voltage. It has the ability to store it. So just like a bucket can't generate a difference in water level, but you could use water pressure to push water into the bucket and have the bucket fill up. And then you could empty the bucket, and that's exactly what we do with a capacitor. So I wanted to show you that once you have it charged up, that's not the end of the story. You can also discharge a capacitor, and you would simply discharge it, well, very quickly. If you wanted to just put 0 ohms across it, it would be just like taking that bucket of water and throwing all the water out at once. So you get a really high surge of current. It's a blast of current, right? Because current is coulombs per second. And if you dump it all at once, that would be a really large current for a very short time. So it's somewhat explosive in nature. You can get a big spark from a capacitor by dumping or discharging all the coulombs at once. A miniature bolt of lightning, if you will. So capacitors have that incredible current capacity that you get by being able to discharge them rapidly if you want to. Or you can control the discharge rate, again, with a resistor, just like you controlled the charging rate with a resistor. We can control the discharging rate. One thing I'm just thinking of now is to see the power that capacities bring to our arsenal of electronics. Picture if you have like maybe a voltage source, and we could picture a little squirt gun perhaps. So it's able to push out water, but not a lot. But you could fill a bucket with that squirt gun. And now picture if you dump the bucket all at once on whoever you're having a water battle with, right? How quickly you could soak that person, as opposed to with the squirt gun. So I mean, again, all these odd little analogies, but I hope they help show you some of what we're dealing with. So the capacitor really does bring high current capability, albeit for an instant, and that's a big thing down the road that we'll look at again. So high surge currents are possible with this. All right, well, let's look at how we discharge it. Like we said, let's do it in a controlled fashion, and that would be to put some kind of a resistor in place to discharge it. And it's a very simple circuit, right? In fact, the capacitor looks kind of like the source now. And then the question, how fast will it discharge? It's the same as how fast would it charge. It's still an RC time constant that tells us that information. So here again, you can just take whatever discharging resistor you have times the size of your capacitor, and that'll give you a time constant, which tells you how many seconds it will take for the capacitor's voltage to drop 63%. Okay, so it's again the 63% distance in voltage, but it's now in the other direction. So to drop 63%, we would actually arrive at a voltage that is 37% of 3 volts, right? Do you follow that? We can draw that. Let's do that next. So yeah, let's try to show that as it would happen on your scope, as you're tracing with a slow acquisition rate. If we use the same 1000 microfarad cap and the same 10K resistor, the time constant is still the same. It's 10 seconds. But in this case now, it's going to take 10 seconds to discharge the cap down 63% of the way to 0. So let's draw that. I'll slide this over a little bit maybe. We'll see if we can get some more space here. Running out of room. All right. So our cap is actually sitting at the 3-volt mark. And then we'll show you a circuit that'll let us do this very easily. But when you throw the switch, you can discharge it. And it'll be that same nonlinear rate. It's going to start discharging rapidly and then slow down, okay? And it'll go all the way to 0. It's going to get to, well, this was 63%, right? 63% of 3 volts. It's going to drop to 37% of 3 volts, right? And I'll tidy this up a bit. Hang on a second. Okay, I've tried to tidy things up a bit for you. So again, we start with the cap at 3 volts fully charged. We connect the 10K resistor across it to discharge it, or in other words, allow the charge on the 2 plates to equalize. And it will start to equalize, and you'll see the voltage is dropping, dropping, dropping. And in fact, from our starting point, as soon as we threw the switch to start it discharging, from that point over to the point where the voltage on the cap drops to 37% of the 3 volts, which is 1.11 volts, it will be 10 seconds to go from 3 volts down to 1.11 volts. That is a drop of 63%, you know, because it dropped, I mean, here to here. That's a decrease of 63%, which leaves us at 37% of 3 volts, which is the 1.1 volt. Okay. The time it takes to do that is 10 seconds. That's the time constant, right? That is the capacitor's size, the bucket size, and times the resistor that's being used to discharge it. This introduction to capacitors exercise is also great at keeping your scope skills developing, right? And we're going to purposely do it with slow times so that you can get the feel for the scope grid, that it really is tracing out voltage in time. And you can see those times. Just don't forget to hit the stop button when you want to freeze and really examine something and take measurements. We might do another tutorial at some point where we can help you with cursors. Obviously, it's going to be nice to be able to bring cursors onto the screen. You can fool with that on your own. It's just hit the cursor button and you can start fooling with that. You can do measurements, like if you want to use cursors to line up on these points, that's great. Of course, more simply, you can just use the scope grid itself, and if you set for something simple like 5 seconds per block, I mean, you'll see 2 blocks of space between the time you started the discharge and the time it arrived at 1.11 volts. You might need cursors for that. But yeah, it is intended, this exercise is intended to help keep developing your scope skills as well. Of course, feel free to watch this video lecture more than once. Take good notes. That's going to help you keep your sanity when you're doing the exercise. Again, simple things, each in their own right, lots of simple concepts at play here, and then you have to be able to put them all together without getting it all jumbled. That is the story of our life as electronics technicians. Just any one thing's not so bad, but 10 simple things and how they relate to each other is the challenge. For these examples, we've used the 1000 microfarad and the 10K resistor, you know, to charge the cap and discharge the cap. And of course, we get that 10-second time constant. Feel free to try some other values of capacitors or resistors or both, and calculate the time constant, see if it all plays out. Of course it will, and you can test your scope skills, you know, scale the scope to a different pairing of a cap size and a resistor, and run the exercise with some different values. That'll be great practice for you. The last thing we have to do is show you the circuit that we'll use to run these little experiments. We'll use the small breadboard like we mentioned. And by all means, do not skip the previous part of this video. I've said it before, I know, but that is deadly. You have to understand it. Otherwise, you don't have any foundations to build on as we layer more stuff on top of this. So please, 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 don't fast forward to the part of the video where you saw the small breadboard pop up and then just try to stick parts on and do it that way. We have a description for that. That's the paint by number approach, you know, if you know those old paint by number paintings. And of course, that's not an artist, that's just a copycat. So you have to always catch yourself if you're trying to just do a lab. The real goal is to understand it. So we want to do things that we understand. We don't want to just copy and make something, you know, happen that we don't understand what's happening, if that makes sense. So yeah, so don't do the copycat style. Don't do the paint by number technician, whatever you want to call it. Sometimes when people say they're a visual learner, what they really mean is show me exactly what to do and then I'll do it. So don't be that person. What we're trying to do is get you to understand something and then be able to do it from your understanding. And that is the technician, and that is the job where you get a paycheck. The other thing is a non-skilled, you know, position where the person that knows what to do, you can maybe get a helper as long as you show him you know what to do, and then you say, here, this is what you need to do, that kind of a thing. So that's definitely a pay grade down. So yeah, for this 2 years of schooling, we're trying to get you into that actual career where you're the person that knows. Pays much better. Okay, pep talk's over. So let's show you the little simple circuit that you can build to see everything happen that we talked about for 30 minutes. You can use those same values that we talked about in the video lecture, 10K, 10K, 1000 microfarads. I think you can see it's just a simple single pole, double throw switch. You have a slide switch in your parts box. Let's use that. And this is the pole. These are the throws. There's 2 throws. So you can take that pole and connect it to the upper throw to charge the cap, right? Then you have a charging path. You've got 3 volts, a 10K, and a 1000 microfarad cap in a simple series circuit. And the capacitor will charge up to 3 volts, just like we mentioned, non-linearly. It'll start fast and then slow down. To see that all happen in real time, put your scope in slow scan mode. Just put channel 1 right here, right? And you'll have to get your scale right, you know, your vertical scale, volts per division, and your horizontal scale be a very slow, you know, certain amount of seconds per division. Don't forget scope common. Scope common is always a thing to remember. It's the little mini grabber to mini grabber coming right off. We're just taking it right off the scope, but bring it to your circuit common. Remember, voltage means nothing if you just have a single point. Voltage is always the difference between 2 points. So your scope, when it's measuring voltage, it's just like your voltmeter. It's measuring the difference between those 2 points, okay? So you have to bring scope common over to your circuit common, and this will play out perfectly for you. It'll just bring it right up on your screen. Of course, we have to start with the capacitor at 0 volts. So if you left it in this position and you put it up on your scope screen, all you'll see is the end result of the capacitor being at 3 volts, and you'll just see a 3 volt trace going across your screen. So I guess the starting point is we would want the capacitor down, we would want the switch, you know, to be in the down position maybe, obviously, so that the capacitor has been discharged. It'll take some time to do that. To get to 0. But once the capacitor is at 0, then you can see as you flip the switch up. Let's maybe you talk through that play by play. So if I have the vertical and horizontal scaling all set for my scope properly, which might take a little bit of fooling around on your part, some experimentation, but get it dialed in, eventually what you're going to have is the ability to then just throw this switch, right? And the cap will start to charge. After 10 seconds, the capacitor will be 63% of the way to 3 volts, right? Because of our time constant. Something I didn't mention before, but after another 10 seconds, the capacitor will have charged again 63% of the remaining distance. Okay, it's actually following what's known as like the natural log. So it's something that happens not just in electronics. It happens with accounting. It happens everywhere with radioactive decay. I mean, but there's this rate where it's going to be a continually advancing 63% of the remaining distance. So after 10 seconds, of course, the first 10 seconds, it's 63% of the distance from 0 to 3 volts. Then the remaining distance to 3 volts, after another 10 seconds, it'll go 63% of that remaining distance. After another 10 seconds, 63% again. So of the remaining distance to 3 volts. Technically, it'll never get to 3 volts, but it will always narrow the distance to where it's at, from where it's at to 3 volts by 63% after every 10 seconds, after every time constant. So technically, it'll never get to 3 volts, but we accept 5 time constants as pretty much having arrived. And you'll see that on your scope, perhaps if you put it at a real slow scan. For us, 5 time constants is long because we picked a long time constant. So it would be 50 seconds of time that it'll take the capacitor to get essentially to 3 volts. Even then, it technically won't be, but it'll be like 99.99 something % of the way there after 5 time constants. And you can get that with math. You can see how close it is if you just would do the math on that. But yeah, so 5 time constants is accepted as pretty much all the way there. So you can see as we run this, little experiment that introduces you to caps, you can see it's going to take some time. I mean, if you really want to see it essentially get all the way to 3 volts, you're going to be waiting a while, If you get a little impatient with that, no problem. You can tweak the values for this experiment. You could take these down to 1K, right? That's easy enough. I could do that. Look what happens, Now I have a time constant of 1 second. So in 1 second of time, you'll get 63% of the way there and so on. So you could play around with these numbers. Of course, I could have done that if I wanted to. I could leave those 10Ks and I would get the exact same I'd get the same 1 second time constant easily just by putting in a 100 microfarad cap instead of 1,000. Okay. We start off with a really large time constant just because it helps you see things in real time as you're trying to stare at it and see what's happening. So, of course, in other circuits, the time constant might be milliseconds or microseconds. And so you would just need a really fast speed up the scan rate on your scope. And that's totally possible to look at the time constant then too. I do like the long time constant though when you're first learning this stuff. It helps you sort of digest it. So throwing the switch up, and you only have to wait 10 seconds for it to get 63% of the way, but you're going to have to wait 50 seconds for that capacitor to get 99.999% of the way there. Once it's there, maybe after 50 seconds, you can throw the switch down then and watch it discharge. And you can see, again, it'll be nonlinear. It'll discharge rapidly at first. As it loses voltage, it has less voltage, of course, to push current through this 10K. So, I mean, the 10K discharging resistor has the same voltage as the cap. The cap is losing voltage. It can't generate voltage. It just stores a charge, which can be depleted by a path put across it. And that's what the 10K is doing. So obviously, as the cap discharges, it loses voltage. And so there's less voltage across the 10K and current slowing down. So they're both happening at the same time. The cap's losing voltage, so's the resistor, current slowing down. So you can see all of that. Of course, it's the same 2 points here, isn't it? And when the capacitor is discharging, it's going to take that same 10 seconds time constant to get 63% of the way towards 0 volts, which is actually 37% of the 3 volts, if you can follow that, which is the 1.11 volt. So it'll take 10 seconds when you throw this switch, from the time you throw the switch to discharge to the where the capacitor drops to 1.11 volts. That should take 10 seconds. It'll take 50 seconds to get essentially to 0, though, because remember, it starts fast, so it only takes 10 seconds to get approximately 2/3 of the distance, and then to get that last third of the distance, whether charging or discharging, is what takes an additional 4 time constants, or 40 seconds in our case. As you use this circuit to learn all the theory stuff that we talked about, you can make some modifications that sometimes make it a little easier to repeat things. For example, if I wanted to look at that charging curve over and over to really sort of see what's happening, and I didn't want to be troubled with the 50 seconds that I have to wait to reset things, I could put a 100 ohm resistor here. And now look, I've got, how long do I have to wait? Only 1/10 of a second, I think, to discharge it. Well, times 5 time constants, that'll get it to 63% down. So it looks like half a second, right? Because my time constant's down to 0.1 now. 5 time constants will get me to 0. So what I'm saying is I can throw the switch to this position and discharge the cap in a half a second. You know, if I wanted to keep looking at the charging curve and seeing that over and over again. Or if I wanted to be looking at the discharge curve over and over again, I could charge it in half a second, right? And by putting 100 ohms here, and then watch the slow discharge with the 10K. So these resistors, here's my charging resistor, here's my discharging resistor, and you can play around with those. Just be careful not, I wouldn't go too much lower. The currents are going to get high. The surge currents get high because remember, you can dump that capacitor rapidly and you get a really high surge current. So we don't want to get in trouble that way as far as what kind of surge currents or sparks start happening. Probably one vulnerable spot is the contacts here on the switch. It would be possible if you had too high of a surge current to just spot weld these switch contacts together. So yeah, a little capacitor is a little spot welder. If you doubt that, or don't quite, or want to see it, I don't know, be careful, but you can take the 1000 microfarad cap and just touch its leads together after it has a charge, and you'll spot weld the 2 leads to each other if you have a high enough current. I mean, don't be careful with it. Don't lose your capacitor over it. Oh, and speaking of that, I noticed they also have the leads on the capacitor staggered. I mean, one's longer than the other to also help you see the polarity. You don't have to maintain that. You can trim that, right, so that they're easier to get on the breadboard. That's one little housekeeping thing. Okay. When you get to this part of the video, do show it to me. I do want to see the capacitor charging and discharging, nicely displayed on your scope. And then this very last part of the video, we're going to just show you how we can add this to our comparator circuit. But make sure right here at this point, call me over. I can see that, you know, that you have it up on your scope and that you're understanding this part of it. So we can add this little circuit that we've used to introduce caps to the comparator circuit that we know, and we can create a little timing circuit, because essentially what we have with the cap and charging or discharging resistor is simply a little circuit, a little voltage divider, even if you want to think of it as that, that converts time to voltage, right? So we'll have our little timer circuit going, and if you can look at it, maybe we can, as is here, this would probably be what you'd call an on delay for this lamp. Let's just jot that down here. And just as the name implies, it's going to turn on the lamp after a certain amount of time, or in other words, there's going to be an on delay. So you have your switch in this position. The capacitor is at 0 volts, which means the plus input of the comparator is not winning. We have some voltage parked here. So do you remember this will be high or low? It'll be low, right? Because the association that I think is easy to hang on to is whenever the minus input is winning, the output's down, you know. And whenever the plus input's winning, the output's up to the 5 volts, to the plus 5. So associate that and associate the minus with the 0 volts, and you're all set. So the cap's at 0 volts, and this input has a reference of 1.89 volts. It's low. The FET is off. The lamp is off. We throw the switch. Nothing happens. The lamp doesn't turn on. But wait, how long? 10 seconds, right? I kept the same numbers here. So we have our time constant that is 10 seconds, because 10K times 1,000 microfarads is 10 seconds. I know the lamp's going to turn on in 10 seconds because I purposely put my reference voltage at the 63% of 3 volt point, which is 1.89 volts. So I know that the capacitor is going to charge up to this voltage in 10 seconds. And immediately after that, it'll go past 1.89 volts. This input will win, the lamp will turn on. So I guess to be perfectly precise, it'll turn on immediately after 10 seconds. You know, it'll take 10 seconds for the capacitor to charge through the 10K, this size capacitor to charge through the 10K. It'll take it 10 seconds to get to 1.89 volts, and then it'll surpass it right after that, which means this wins, which means this goes high, which means the FET turns on and turns on the lamp. So that's what we would call an on delay. You want to turn the lamp off, throw the switch, it'll turn off pretty quickly. Essentially right away, I mean, kind of, sort of, but actually it'll take a little bit of time, right? 1/10 of a second to get maybe, well, we got to be careful here, right? This is a little tricky. We have to think about when it would fall below 1.89 volts. So let me do that for you. It would actually, we don't have to concern ourselves. We're trying to make it just so that it goes off essentially right away. If you really wanted to split hairs though and look at it, you'd have to say the time constant is now 1/10 of a second. It won't get to 1.89 in a 1/10 of a second. It'll get to 63% down from 3 volts. So it'll be at, in a 1/10 of a second, it would be all the way down to 37% of 3 volts. So it'll get below 1.89 volts faster than a 1/10 of a second. And we could do the math on that, but you don't really care to do that right now. What our intent is to put a quick discharging resistor here. So essentially when you throw the switch down, the lamp turns off. And then when you turn the switch up, it takes 10 seconds to turn on. Because we have the rising charging time constant here, the voltage level that it'll get to in one time constant when it's charging. We put that here. Yeah. Okay. We can just as easily make an off delay. Piece of cake. Just switch these resistors, right? And now when you throw the switch up, the lamp will turn on essentially right away. Very low charging resistor. So 1/10 of a second-ish, it'll turn on. So on right away, but when you, and that means the cap will charge up very quickly, essentially right away to 3 volts. This wins, the lamp's on, the FET's on. This is high, the FET's on, the lamp's on. And then your off delay occurs when you turn it off, which means you throw the switch down, but the lamp stays on for a prescribed amount of time. Our prescribed amount of time is 10 seconds. You could have this be minutes. You could have it be, however much time you want. Ours, for demonstration purposes, is a little 10-second delay. So you turned it off. It's going to stay on for 10 seconds, maybe for reasons that you'd like, and then turn itself off. But it gives you 10 seconds of light and then goes out. That should happen, right? But we have to do a couple adjustments here. We've got a 10-second time constant now for the discharge path. Can you see what we have to change? We've got to adjust this, right? This has to be now, it's going to be discharging, so it's going to go 63% of the distance towards 0, which means the voltage it's going to get to will be 37% of 3 volts. So that's why we have to change our reference voltage if we want to do the off delay. Let's put that in. I think, what was it? I think I remember it was 1.11 volts, right? That would be it. Now, the accuracy of these little demo circuits is also going to rely on the 1000 microfarad, how spot on is that? So capacitors do have a wide tolerance. Some of them can be like 20% tolerance, typically, or 10%. So, how spot on is it as far as being 1000 microfarads? And so you don't have to worry too much, but we're going to get, the demonstration. Whether the numbers are off a little bit, that would probably be because the capacitor's value is off a little bit. And I forgot to mention it, but of course we want to be watching all of this with our scope, and we have 4 channels, so we can really get this circuit under our thumb, right? It's channel 1 can be watching the cap, charging and discharging. It is the capacitor's voltage. It's also the plus input, the non-inverting input to the comparator. Channel 2 is watching where we have our reference voltage set, and of course these two are a nice visual on your scope. They always keep you straight as you look and see which input is greater, which one's above the other, which of course determines whether the output is high or low, which is monitored on channel 3, which of course determines whether the FET is on or off, which is monitored by channel 4. So you're really turning into a technician already now when you can get a 4-channel scope to just be scrolling across the screen, showing you everything that's happening in a circuit like this. The game doesn't change all that much. This is it. You are arriving as a technician when you have scope skills and an understanding of voltage, current, resistance, and how things are behaving. It's sort of a microcosm. It's a miniature example of exactly what it's like to arrive at being a technician. Your eyes into the circuit are through test equipment. Your understanding, of course, has to be there too. So you have to have the theory in your head, and you have to have the test equipment showing you what the circuit's doing, right in front of your eyes. And then they have to match up. And finally, if you want to, you could just pick that midpoint from way back in that video lecture. We had mentioned it that you could put the reference voltage right at 1.5 volts. Do you remember what that does? Now, whether you have an on delay or an off delay, the timing, it won't be a time constant thing, but it'll be 0.7 of the time constant. So 7 seconds. So if you want to just create the ability to make an on delay or an off delay without having to change the reference voltage, you could park it in the middle, and it will now be the time, the on delay time or the off delay time would be 7 seconds with these values in place. So right now I'd have a 7-second off delay, thanks to this. I didn't put it at 63% or 37% for an on or an off delay, but I just have it parked in the middle. So this, again, you would now expect a 7-second off delay, as it'll take 7 seconds to get to 1.5 volts down from 3 as it discharges. Or again, you could change these that'll work for either one. And it's just, you know, another way to fool with the circuit. You know, now I've got an on delay, and it'll take 7 seconds to turn on because it takes 0.7 times the time constant. That's how many seconds it takes to get to halfway on the voltage. Yeah. So yeah, it just keeps you from having to change this if you found that annoying. So many ways you can fool around with it, as far as, you know, creating what you want to create. But the main point of this whole exercise is, of course, introducing caps, and this in a DC context, as they charge and discharge, you get to see that. You get to keep working on your scope skills. So all good things. When you do get this part done, show it to me. What I'd like to see is an on delay or an off delay. I don't have to see both, but I mean, pick one that you like the most, and then call me over. I'll have a look. And I want it to be scaled on your scope that we can prove everything. Like if you would have this 7-second delay perhaps going, have it so that we can freeze the scope and see those 7 seconds that it took for the cap to rise to 1.5 volts, and then have the plus input win and the light turn on and all that good stuff. That's what we'll do. We'll just freeze it on your scope, and we'll check you off that way. And one last reminder, please, please don't go to the last frame in this video and just try to do this. I'm chuckling now. I might not be chuckling as I hover over you at your bench. There might be smoke coming out of my ears at that point. So yeah, don't do that. I suspect some people are, and then, you know, it's hard. I mean, these videos aren't meant to be able to take the last frame and just put that thing together like a hobbyist. You got to understand it. And of course you have to understand it because we're going to be building on top of it. So please, please, please.